Okay. Is it better now? All right. So we are three guys from LigoWave. I'm Jonas, then Thomas, and also Gedrus. And I'm a person responsible for marketing. I used to be in sales, but now downgraded or upgraded to marketing. And then Thomas and Gedrus are developers. Thomas is, I would say, a software architect slash developer slash support engineer. That's where he started his career in our company. And then Gedrus is, he calls himself low-level software developer. Right. So then a short story about our company and what reasons are behind it. So our company evolved from a wireless ISP, which was established back in 1995, which was about, not about 20 years ago, long time ago. I was 9 years old back then. And yes, from wireless ISP, within this wireless ISP, there was always a group of Linux developers who did some development on different wireless systems used within the product range of this wireless ISP. And then from that, well, a company called Vilubox was born. And Vilubox was doing software development for various hardware platforms. Vilubox was established back in 2005, so about 10 years ago from now on. And then in 2007 we realized that having our own software is not enough. We need hardware as well. And this is when LigoWave was started. And LigoWave from its original shape, I would say, changed a lot. If to look at it, what it is now these days, because it's a, I would say, quite a reasonable size international company. Our headquarters are in US, and then our R&D office is in Lithuania, in two different cities. We have office in Kaunas and in Vilnius. And in Lithuania we have now more than 50 people, so at least half of them are software or hardware developers. And then in this Lithuanian office we do software development, we do hardware development, so we do digital design, RF design, then we also make our own antenna designs, we design our own enclosures, even the packaging which the devices are shipped in is done in the office where we come from. And then everything is built in our factory in China and then shipped worldwide. So at the moment we ship to 95 different countries, and rough estimate, well, last year we shipped more than 200,000 devices. This year we expect to reach about 300,000. Right, so this is a short introduction to our company. And then, of course, what's also important for your community, I guess, is the variety of devices that we are selling. So at the moment, the latest products that we have announced a couple of months ago is Ligo DLB products. And on this product line, we have a variety of devices with different antenna gains and characteristics. So the first device that you see on the left is the DLB290 and DLB590, which is an integrated 90-degree sector antenna device, ideal for the base station scenario. And then also there's the DLB2, DLB5 device with the external N connectors. This is a universal device, but in most cases it's used for a base station or long-range point-to-point links. So this is something similar to Rocket from Ubiquiti Networks, except that It has more professional antenna connectors, IP standards rated enclosure, I would say more professional mounting, grounding option on the device, and also a better software inside. Then DLB214, DLB520 is a medium distance device, I would say, which, well, according to our lab tests done in Lithuania, runs about 100 megabits throughput on a 10-kilometer link. This is not what we've seen here, but I'm sure we'll be able to solve this soon. Then also DLB29 and DLB515 are our, I would say, latest design devices. Gathers, if you can pass this to everyone, the 515, or both of them, yeah. You both, yeah. Thanks. Yeah, those are small, I would say, low distance point-to-point, point-to-multipoint communication devices, and what's important about them is their size and their price too. Then DLB29, 529B and 515B, it's similar devices to the prior one, except that their enclosure is more robust, more weatherproof, it's IP65 standards rated, and then enclosure is used from our previous generation products. And then also two longer range devices, which are DLB Mach5 and the DLB Eco5. So the Mach5 has an integrated directional 23 dB antenna, and then Eco5 is sort of, I would say, an interesting device because you can use any kind of offset dish antenna with it, which is available in the market in your country. So in the places where, let's say, logistics take a large portion of the cost of the product, this is really important. And in some like third world markets like India, Brazil, this is a great device because you can ship them very efficiently, and then there's lots of antennas made locally, so they can make long range connectivity without any problem. Yes, and those are some. Yes? Yes?
Short, medium, and long distance. How far is the short distance and medium and long? I have no idea. It's the next slide.
Yes, it's yeah, actually the next slide. So here you can see our devices, like what sort of distances we support in a point-to-point and point-to-multipoint connectivity. So with the Eco5 on a point-to-point, you can still reach about 100 megabits on a 25-kilometer link. This is the longest we can go on a 100 megabit link. But of course, we've seen some much longer links than with our devices. Not exactly from this product line. We have another product line called LigoPTP, which is dedicated for the backhaul connectivity. And then with these products, I think the longest one we've seen was in Thailand.
Yeah, it was 110 kilometers.
Yes, 110 kilometer link, and on this link, this was with 34 dB dish antennas, and they got about 70-80 megabits of throughput. So still quite a decent throughput on such distance. Yes, and also some latest stuff from us. We have just released a new bracket for the Eco5, which can turn it into a small size, attractive form factor CPE device with a 15 dBi gain antenna. And what's nice is that the enclosure still retains the weatherproof rating, and then it's metal, so it doesn't get that much noise from the devices that are surrounding it. It's easy to align, and then if you need a short haul 100 megabit link, that's an ideal device in terms of form factor, size, and reliability as well. And now I will, yes? Well, temperature, we use a thermal chamber to test what the temperature that devices can survive during the development phases, and our devices can go, I think, from -40 to +65 degrees Celsius. Okay, then let's move to more interesting part that our developers have to say, so I'll pass the microphone to Thomas. Okay.
Better if I hold it. Okay. So at the beginning we had different kind of chipsets. For example, in the 2 years ago, the main chipset in our products was based on Relink instead of Atheros. So as we grew up, we decided to switch to Atheros-based chipsets. And the common motivation for this was to build more scalable, more stable multi-point links, as well as point-to-point links. So we started to develop, I would say, proprietary protocols, which is quite common between vendors. Ubiquiti has TDMA, at least that's what they call it. MikroTik also has something similar to the TDMA, and so are we. So the very first version of IPOL1 was based basically on Relink chipset. It was based mostly on round-robin fashion. So in other words, you have many clients, for example, around 50, and they are polled with different transmit queue length based on the modulation data rate as well as packet loss are polled in round-robin fashion, so each by each. And the structure was quite easy. We had tokens. In other words, if you don't have token, you cannot send. If you have one, you can pass. But as our customer base grew, we had to increase this performance because some of the clients decided to connect 100 clients to the access point. And as we know, each round-robin poll increases the latency for another customer. So we decided to improve it a bit. One of the first improvements for IPOL1 was quality of service. Since that quality of service was based basically on software side, no hardware queues were used, we had quite a performance decrease when you enable the quality of service because all the packet delivery to different queues was based on CPU power. And when you have 100 clients, that CPU is eaten quite fastly. Not only because of the quality of service, because we also have to deliver statistics from each client. Because when you have 100 clients, you have to gather statistics each 10 seconds. At least that was the way on the first version of IPOL. But because IPOL1 was relatively close to hardware, it performed quite well in highly interference zone. And due to this, it was quite successful. Later, as we switched to Atheros-based chipsets, we did another IPOL V2 version. It was a more complex version because we improved the stability against the interference by increasing the number of tokens which were attached to data packets. Because we noticed that, for example, in IPOL 1 version, when you have only one token, which is indicator for sending or receiving packets, usually due to interference, we lose those packets and the station cannot be polled at that moment. So only next cycle, only in the next cycle. So we did a bit differently in IPOL 2 version. And what we did even more, we created a scheduler with different type of clients. Some of the clients were split in two groups. One group was active clients and another was idling clients. In this way, we polled more frequently clients which were active, had more data to send, and had higher modulation level. This increased our performance with operating with more than 50 clients connected to single base station. Additional improvement was that we moved the proprietary driver from hardware to software. This wasn't quite a good idea, but it was fixed in the third version of IPOL 3. This version is a hybrid mode between the older one versions and 11N based protocol, because we moved IPOL 3 closer to low-level driver, which increased our throughput as well as decreased the latency which each device received. Currently, it's in alpha stage, almost beta stage, since we currently are developing this proprietary protocol, and we are working currently on multi-polling solutions. So, in other words, to decrease the amount of tokens required to poll multiple stations. So we would have more airtime for active clients and less airtime for idle clients. We also have full quality support, which is, you can say, based on hardware instead of software. So quality of service is VMM, which is standard for 11N. And this gets us quite a good performance figures. So all our protocols are tested in different environments. For example, the picture on the left with TV monitors is used to test the triple play solution like VoIP, IPTV, and normal data. So IPOL 3 was tested in this kind of environment with 20 clients, and we checked how the quality was with streaming VLC HD channels on real operator, which was quite recently in Russia. We also have a testbed which has 64 clients connected to a single access point via attenuators. And basically, this is our main environment where we develop and test our new ideas. And last but not least, we have a full outdoor setup connected around 61 clients. The distance between clients and access points is 200 meters. We use this primarily to test interference to our protocol and see how it interacts, because we noticed while developing that Atheros-based auto rate is more used to indoor than outdoor, and depending on the distance we had to tweak it, in other words, rewrite it completely. So Yeah. So this is our latest setup, 61 clients. And we usually do benchmark to compare between MikroTik, Ubiquiti, and our devices. Same amount of devices, same conditions, and we measure different parameters. So at the very first beginning, we started with 30 stations performance report. We compared IPOL 1 to IPOL 2. As you can see, IPOL 2 performs quite well compared to IPOL 1. The latency was decreased due to a different group of clients, and we achieved far better results on different levels. Yeah. We also measured performance in noise environment to compare 11N and our IPOL protocol, and as we can see, we get a bit more throughput compared to 11N. Not a bit, but quite a huge margin. So we continued the test with 61 clients. We compared IPOL 2 to IPOL 3. Since IPOL 3 is more hardware-based than IPOL 2 and uses all the possible hardware solutions from Atheros, we increased the throughput even more, and latency is 4 times less than IPOL 2. So basically these results are for multipoint. And Giedrius will tell you about our recent works in point-to-point solutions.
Google application. Is it okay? Yeah. Can you hear me? Okay. So hey guys, even though the slides are gonna be about the device or a project, but it's really a story about me and my problems. So it all started back in, I think, February, when my boss asked, can you make double throughput? Well, could you double the throughput? And I was, and well, I still am naive enough to say, okay. And so that's how it all began. And currently we call it, well, there are quite few names. It's really in a prototyping stage. But one of the names, what we call it, is COBRA. So it's an abbreviation for combined radio. And what in its basic form, it is a host device which has 2 PCI radios, 11 AC radios, which are modified in a way that they would work concurrently. So why should we do that? Well, first, foremost, the most important, and well, that's important enough just to be one reason, is to have a higher throughput, much higher throughput. But as a side effect, you get our good properties like link redundancy. You also can more efficiently use the bandwidth. You can combine 2 channels, and one can be 40 megahertz, other can be 80 or 40 and 20. Well, basically, if you see a gap in the noise, you can go there. Well, also from our solutions that they use, you also get the collocation capabilities, well, and other good stuff. So anyway, it all up to this point sounds easy enough, but there are few main problems, or there are a lot of problems, but few main that I had to solve, that you have to solve, is, well, first, I'm gonna go in the most important fashion. So first is the local transmit coexistence. Because these radios, they are connected to the same set of antenna. Basically, what you see from the outside, you have one device, you know, one Ethernet and one antenna. just two radios that they are combined, connected together. So if you have, well, the best case scenario, if you don't have the transmit coexistence, you have the incoming packet and the other radio, even though that it is in the other channel, due to the wideband property of the amplifiers, you basically hit down that packet. It's corrupted. That's the best case. The worst case is that you actually burn the amplifiers because they're not protected. So if one radio is transmitting, the other should transmit or at least be in the kind of preparation for transmit state. Basically switch its logic. So that's the first. The second goes for the efficiency, and that is local transmit, remote receive synchronization. I mean, that's that's really important for all the devices. I mean, if I'm sending, then the other party shouldn't be sending. I mean, we have to synchronize somehow. I'm sending, you're sending, I'm sending. So, but it really becomes especially important here when you have two radios, because if you're not synchronized good, you're not losing one packet, but at least two in that case. Okay, so that goes for the efficiency. Now the third one is the third one follows from the first two. Actually, if you think a little bit, is that you can't have hardware acknowledgements. Basically, you have to turn it off, and when you turn it off, you have problems with protocols like TCP that rely on reliable packet transmission. I mean, with UDP it would be all right, but with TCP it's a kill. Okay, and the last, when you have two radios, you basically have three interfaces, one Ethernet and two radio interfaces, so you have to do some kind of bonding. Okay, so next to the problem, so could you?
This also uses the Atheros chipset?
Yes.
Yeah.
PCI radios are there.
11 AC.
Yeah, 11 AC.
Peregrine you used.
Yes.
Peregrine.
Yeah. Peregrine, yeah. Yeah, it's Peregrine radios.
Peregrine itself will has a dual radio, right? It will operate on 2.4 and 5 G in the radio itself, right?
Could you repeat? I'm not quite sure that.
One radio.
No, one radio only, but in Peregrine you can operate on both 2.4 and 5 G.
Well, there are several. The Peregrine is really the core. I mean, the CPU that is running inside, and you have several actual chips, but you may be able to operate on two bands. Like you can use the same chip to operate on two bands, but when you deploy the hardware, it's either one or the other. So unless you do some kind of smart switching, but I haven't heard that anyone would do that. Okay, so the first problem, transmit coexistence. At first I thought maybe hack a little bit the Bluetooth, the coexistent module, but it turned out it doesn't work that well, and it wouldn't be enough. It wasn't fast enough. It's using the inside software, stacks layers. And what I've come up with is a custom GPIO handshaking between the two radios, just align, and there's I know, maybe you could call a protocol. It's really a handshaking more or less, and also had to find a certain set of hardware registers that could efficiently turn on, turn off the radios without crashing it, or just basically a fast stop that wouldn't invalidate the radio. Okay, so
Our next version of the chip will support all those things.
yeah,
I'm working in Qualcomm at the moment.
yeah.
So Peregrine we don't have the support, but our next version is called Bayliner. So like we are multiplying the bandwidth in two. We are doing the same transmission on like the chip inside is a two radio. Okay,
Yeah.
so at the same time, whatever data is coming, we will split it and send it to the two radios.
Is this the second generation AC radios?
They do that.
So they are actually two radios, two cores?
But outside it looks like a single radio,
Yeah, one chipset, one sock.
chip.
Yeah.
But inside it has a 2 radio. Okay, so
Yeah.
whatever data is coming, we will split it and send it to the 2 different.
Yeah.
So that is our next version of chipset.
Okay, so it's similar. Okay.
That is called billionaire.
Okay. When is it coming out? Available?
It's released to some TP-Link and Netgear, like they are prototyping for that. They
Okay.
under, but it's released on January only. Our first CS release in January.
Okay. Okay, so the next problem, the remote synchronization with the remote. So I took the fast path. I bumped in a microcontroller, which acts as a TDMA manager, and I synchronized the local and remote managers using a GPS for future purposes, like if you don't have a GPS signal or other reasons. We're thinking about implementing a IPOL-like protocol. Maybe, if need be, go to something more exotic, like high stability crystal synchronization. So some of the results. This is a snapshot from a digital analyzer, and from the bottom 2 rows, you can see on one side, local side, you can see the actual packets and how they are coming in bursts, and the arrows, they point to the remote and local synchronization. I mean, if you look at the edge of, well, in the top, the arrow to the top, it shows to the peak of the transmission of the remote side, and the bottom arrow points to the switching to the receive, local receive. So they are each one transmits and the other is almost immediately to the receive. Okay, so the acknowledgement mechanism. What I did is implement a custom block acknowledgement. And its improvement, well, it's more efficient than the 11AC block acknowledgement. Ours is capable of 2,000 MPDUs, well, acknowledging 2,000 MPDUs, and also for that I had to redo the retransmission and the receive reordering stuff, because that was only for the 11AC standard, so all had to be changed. And for the bonding, I didn't come to this part yet. It has, well, it will be implemented, and it will be a coefficient based, because you can have 2 links that have different throughputs. I mean, it can be even on different bandwidths. So it has to be a coefficient based and adaptive, because you can have changing the throughput on the fly. And for the test bed, I'm replacing the bonding with VLAN tagged packets, and, well, the basic software and what's usual when developing the RF devices is spectrum analyzers, digital analyzers. You know, for the throughput you use like NAPIM, iPerf, tools like that. Also, we have dedicated hardware, Anritsu network traffic generator. So all that kind of jazz. Okay, so the achievements, yeah, that's basically what I said, but the results. Okay, so the first 3 are the actual results. So in the 20 megahertz channels, when both radios are on 20 megahertz channel, MCS8, that's the maximum that you can get. We're getting about 250 UDP, a little bit less TCP throughput. For 40 megahertz, it's somewhere to 650 and 600 TCP. And current at the 80 megahertz channel, the MCS7, it's 1 gigabit of UDP and 900 megabits per second of TCP throughput. And there are still some problems with 8 and 9 MCS. Traffic is not stable enough, but that will be sorted soon. So the expected should be somewhere out 1.3 gigabit UDP and 1.2 TCP. That's duplex. If you have a simplex, then the Ethernet is actually the bottleneck, and you have 1 gigabit. And yeah, you can see the slide of Anritsu, snapshot of Anritsu, it's generating 1 gigabit per second simplex. So, thank you.
Just before a question, I would like to thank the LigoWave team first for supporting this event, and also for bringing all the hardware and sending it over so we could have play with it, take it apart. Add OpenWRT support, so thank you to every one of you who played with it and worked towards the OpenWRT support. Also Dan, who's not here. So yeah, this should run OpenWRT very soon for you, so you can start using it as well. Now, yeah.
With cake. As soon as it's upstream.
So yeah, now shoot any questions, maybe mention SDK and things like that. And let's see where where the community and the industry can coexist.
So these things look pretty amazing. So very good. Can we use that in OpenWRT in one way or another, or is this like only closed software? Do you plan?
Which product exactly?
Yeah, for example, the iPod stuff. I've heard many people asking to have TDMA things in OpenWRT, also with other routers, and I mean that's mostly a software feature as far as I understood from your slides. So do you plan to release that, or is it open source? Or?
Well, IPOL is a proprietary protocol. I mean, that's what we use to compete with Ubiquiti and other sellers, manufacturers.
Okay.
So,
the old versions, or are you considering open sourcing at least the old versions when you start using new ones?
we haven't heard this question yet. So,
like, because if you have a newer version, probably you have it because someone else figured out how to make something better than your previous version anyway. So.
In general, we have some sort of SDK available, which we are giving to other partner vendors that are using our equipment in some scenarios. So I think we can try with some of the developers as well. What worries us most is the support, because our SDK is, well, it's not that much documented, and then once some additional development is done, we get too many questions. And we had this this kind of exercise in the past too, which that's the reason we sort of started hiding it under the table. But then, as we see interest now, let's try and do this again.
Yeah, I
see
think
what happens.
that would be really nice. Yeah. So even if you give a not so much documented version of, let's say, the previous version, and make a license like GPL and just have a big block of source code, that would be perfect. And someone else who wants to try that could start implementing it and either ask questions or try it on their own, but it's really have something, because there were many people asking for it.
What about using FreeBSD? FreeBSD has TDMA, as I know.
No, but it's TDME support in BSD is very limited. And
Yeah, that's what Arvin shot me years ago, I guess.
and well, is this the question of you asking for the drivers that could be, well, for the WRT, or is it just the SDK to the access to develop applications or configurations on our devices that you could use?
I think, I don't know on what basis you implement that, so if it's on the FRS
Yeah. Well, what we get is a proprietary. We get the sources under the NDA with Qualcomm.
So you get the Qualcomm original driver?
Yeah, we have the
successor of Map Wi-Fi.
You will get LSTK or OpenWRT based
the new Qualcomm is on.
QSDK.
Yeah, QSDK, but it's quite recent, so
It's recent one. QSDK is a recent one.
yeah.
You are using a reference port is AP148 or 130?
We are starting to develop on that, but that's the first steps on the QSDK. Yeah.
I think that would be actually a problem because you can't release just Qualcomm's code
Yeah.
because that's your basis. What I'm asking. Only if we have one developer who's porting that stuff to ATH9K and has NDAs with Qualcomm and the equalizer.
Yeah.
Probably work.
Well, we have, as I understand, Qualcomm guys. So, what's the status of the legal status of the QSDK of the new?
Actually, the current status is like they want to screw up Broadcom.
Yeah.
They want to release into open source. Because open source, their recent implementation of firmware has the ME-MIME.
Yeah.
So that's the toughest part. They spend a lot of time to research on it and develop the ME-MIME. So as of now, they're not interested to release that ME-MIME code. It's in the firmware. Because Broadcom is literally expecting us to release that to the open source. They can copy it. Okay, so there's a secret receipt they implemented it
Yeah.
for ME-MIME mode because till Broadcom is not able to do ME-MIME. So until the chips comes and they become a market leader, then they will release.
Okay.
Internally, we have something called App11K, our driver and the firmware. It's going on that project.
Yeah. So that's more than that.
Maybe if you can put out your iPhone stuff and make a proof of concept on top of ATH9K, for example, then you can release that without worrying about Qualcomm at all.
Yeah, even just a formal specification of the protocol good enough for someone to implement and be compatible, that would be amazing. Because that would be like a base for development and also portability of different chipsets.
Well, I can't answer. Well, I don't. Well, not that I can't. I don't know the answer. It really depends. I mean, none of us like really with the iPol 1 development. Well, not hands-on. So I don't even know how much work that would be. Maybe a lot, maybe not. That's really. I'm sorry. That's really something that we should, discuss inside.
But if you do, it will really increase your street cred.
Okay. Note taken.
So this is a proprietary iPol whatever protocol.
Yeah.
Yeah, so there's really two ways that kind of solve our problem. Ideally, we use our team, we can put any of the routing protocols, any of the scripts, and hopefully get decent performance on that. And yeah, the main bottleneck is point to multipoint. The other one, as mentioned through SDK, is as used to be with Ubiquiti, is we can insert the routing protocols somewhat in it. It's still better using devices than not having the brick mode, at least doing some routing in the mesh. So yeah, that's the least optimal but still a helpful solution. So we can kind of think both ways.
Okay.
I have another question in regard to iPol, because I saw that you now implemented it and also on the dual radio timing things. They're implemented on the ATH10K chipset. So supposedly this has like a small Extensa CPU running on it with an internal firmware, which could actually allow you to develop this kind of microcontroller. Supposedly microcontroller-like real-time code in a quite comfortable C development environment, and also probably byproducts of that could be useful for other things. How well is the internal chip, like
Well, I got a bit confused on the IPOL and the Extensa. IPOL is not on the Extensa. I mean, were you talking about the Cobra, the combined radios, or just Extensa in general?
As an implemented, how much does it depend on the specific radio implementation or specific chipset implementation, or is it like an additional microcontroller, or are you actually implementing that as an extension into the internal firmware of
It's an extension to internal.
Sorry?
It's an extension to internal.
Very nice.
So maybe for the gigabit products, what price ranges are you aiming for? The figures?
Gigabit, the last one you mean?
Yeah, so Cobra. That's
It's a prototype, so hard.
But still, like,
Well, we are chasing,
you're chasing airflow.
you know the guys. So it will be somewhere in a similar range,
Okay.
like Ubiquiti, Mimosa.
800.
That would be good. But so a more realistic question would be what, so how high density of such links would you expect in, let's say, an urban environment? So because, you only have 5-degree beamwidth with devices, or maybe 1-degree beamwidth for especially short links. How dense would you expect them to be able to coexist at that frequency?
That's really well. From one point, it's really a really hard question. From our point, you can look at it really simply, and all of these, they're fighting just for the time domain. Well, in any essence, it always comes to the time. I mean, how much time you have to transmit or receive, and well, it's really for a better quality links. I mean, in crowded, I doubt that it will. In crowded, and it's not really something like indoors product. No question about that. I mean, currently it's headed point to point with ability of point to some points. But
For example, the highest number of links we've seen done from one location with our current point-to-point devices is 10. So there was one pole somewhere in Suriname, I think, a 10-meter pole, and then were point-to-point links pointing to different directions, and he had 10 antennas on that, operating without a problem.
Another way might be to use GPS collocation option. I mean, to share the medium between different point-to-point links on the same frequency.
Yes, assuming you control.
Yeah. They all, in essence, have to be the same. Then you have to have some kind of crosstalk, So.
So this board has a GPS sensor also?
Excuse me.
Board has a GPS sensor also?
No, these no.
Okay. What's the purpose of using GPS?
To synchronize the transmission.
Oh, okay.
For the clocks, and well, it also you can use for collocation, and if you have a protocol which tunes its parameters depending on the distance, so the better quality of your measurement of your the distance, the better you can do that. And not only distance, because in the drivers you can find something like location measurement, distance measurement, something like that. Well, it has its limits how accurate it can be. But even the absolute position helps when managing larger networks. I mean, you immediately get a point on your map, so.
So we are using any protocol to, like a separate protocol to find that station's GPS location, because our mobile phone has a GPS. So you also have some GPS. Then you can easily find the location of the mobile phone, and based on that you can take some
Yeah.
formula.
Yeah, but
Yes, I think these were timing.
yeah. For this case, the primary is used for exact frequency and the phase synchronization of the TDMA manager. I mean, it switches really really fast. I mean, in a sub-millisecond. I mean, in less than, well, a fraction of a packet. So yeah.
So given that the sequence to noise ratio is appropriate, there is no degradation in speed over distance.
In theory, yes.
Actually, there isn't, because we use the channel emulator to test different vendors and how they react to different distances. With Apple, for example, the maximum what channel emulator could do was 300 kilometers, and it's still connected and still pushed almost maximum throughput. Because there is no acknowledgement packets, I mean those hardware-based, it still operates even on 300 kilometers. So only signal is important.
Yeah.
Yeah, with regard to the multi-radio application, I saw that other companies came up with a multi-radio based solution to serve a high amount of simultaneous Wi-Fi clients, namely Albarian / formerly Radiant, claims to have solutions serving like up to a few hundred simultaneous wireless clients from a single pole, like supposedly mounted outside a student dormitory, for example. Like that's their primary case. So that's obviously different from the application you're intending to do, but I can see that it could be also a useful application for a synchronized multi-radio
Yeah.
device.
Well, yeah.
Any research towards that direction? I mean, obviously most of the clients are not AC capital or even A capital by now, but they might be in a couple of years from now.
Well, mostly we've been targeting the point-to-point, point-to-multipoint, and the indoor. It's fairly recent. Well, it's not really recent, but fairly recent, you know. So yeah, it could be used like that. I mean, usually each radio has a limit, and well, it's logical. You put more radios, you get more clients. But well, this case, it's not this case. I mean, right now we're aiming for mainly throughput. Like, I mean, in general, I'm an engineer, and engineers are all about the numbers. So.
Okay, I think that's also. Thanks for listening. Thanks for your time.
Yeah.
Hope you like our products.
Great that you came here.
Yeah, thank you guys too.
Така пък, кой е да се минам?